Hi, I'm Bob Musgrave from the Geological Survey of New South Wales, and I'm going to talk today about the geophysical evidence for what makes up the basement of the Macquarie Arc and the implications this has for the tectonic setting of the arc, particularly in the late Cambrian and early Ordovician. So, to begin, some background. The Macquarie Arc is the Ordovician calc-alkaline volcanic system in the Lachlan Orogen. It's noteworthy for having continental-derived contemporaneous turbidites on both flanks of the arc. Volcanic activity in the arc was terminated by the Boninitic orogeny that spanned the late Ordovician to early Silurian. In the aeromagnetic image, strong magnetic highs in red mark the volcanic arc, and these are sourced from deep magnetic edifices in the upper crust, partly matching and partly offset from the outcropping arc. These magnetic highs, however, are superimposed on a broad regional magnetic low, seen as the wide blue areas extending beyond the arc. There are a range of proposals for the tectonic setting. These include west-dipping subduction with advances and retreats of the subduction zone, models which involve east-dipping subduction during at least some part of the arc's activity, competing models which suggest an allochthonous origin as an originally distant arc on the Paleopacific emplaced by abduction onto the margin, or the most radical variant where the Macquarie volcanic system was a back arc to a distant subduction zone. Most of the models for the Macquarie Arc focus on the issue of west versus east subduction below an essentially linear north-south striking arc. Aeromagnetic imagery displays evidence of curvature in the western and central Lachlan Orogen, and this prompted a rethink of the origin as a 3D system that evolved over time. Ross Cayley's Lachlan orocline hypothesis sees that curvature and accompanying strike-slip faulting as the reaction of the subduction system to choking by the Selwyn blocker, a continental fragment. 3D evolution of the arc has also been invoked to explain the distribution of turbidites. Note the relationship here between the Macquarie Arc in the early Ordovician and an extinct Boninitic infant arc. I'll return to this. We'll now move on to a closer examination of the deeply sourced geophysical data to investigate the nature of the arc basement. Returning to aeromagnetic data, you can see the contrast between the Macquarie Arc, with short wavelength, that is high gradient, magnetic highs setting long wavelength magnetic lows, with the Wagga belt and other parts of the central and southern Lachlan Orogen, which are marked by broad magnetic highs. We can highlight that by selecting the long wavelength components by applying a 20 km low pass filter. The regional magnetic low over the Macquarie Arc is similar to what we observe over the Proterozoic Gondwana craton, which is formed by continental middle and lower crust, which is typically intermediate in composition, averaging granodiorite. A low regional magnetic field over the Macquarie Arc is inconsistent with morb, or similarly mafic material, as a major proportion of the middle crust below the arc. This is significant because existing interpretations of potential field and seismic data have inferred a morb basement for the arc, and the apparent consistency of this with geochemical evidence of an intraoceanic character has led to many authors accepting that a morb substrate floors the arc. I am currently producing a series of potential field inversions over the Lachlan Orogen, using part of a statewide 3D model as my reference. Here is one that spans the Macquarie Arc. As I mentioned, previous geophysical models for the Macquarie Arc suggest a morb basement, but the basement, unit 1 of the model, is poorly fitted by typical morb characteristics, with effective magnetic susceptibility in the 1000 to 2000 by 10 to the minus 5 range, and density greater than 2.785 grams per cubic centimetre. The basement, in fact, is better fitted by properties more typical of an intermediate rock, density of 2.685 grams per cubic centimetre and susceptibility between about 100 and 400 by 10 to the minus 5. Similar compositions have been noted as characteristic of the middle crust below mature oceanic arcs, for example, the Izu-Bonin arc south of Japan. We can also examine the middle and lower crust by looking at P-wave velocity from the AusLAMP seismic model. We'll fade in the 25 km depth slice, and you should note how the low regional magnetic field corresponds to an area of low velocity marked by warm colours in the seismic image. Note also the transverse structure corresponding to the Lachlan transverse zone, which hosts the porphyry copper systems in the arc. Yet another approach is to look at conductivity model derived by Alison Kirkby of GA from the AusLAMP magnetotelluric array. This yields a conductivity model from the upper crust to the base of the lithosphere, and amongst other features, conductivity highs, warmer colours, mark both the Macquarie Arc and the Cambrian Staveley Arc. As we migrate down through the crust, the highs associated with the Macquarie Arc persist, although their shape alters a little. There is no evidence of a contrasting low conductivity basement, as we might expect if there were a substantial morb crust surviving. We'll move on to the tectonic implications. So, applying the criterion of an intermediate basement from the Macquarie Arc, what classes of tectonic models would this allow? It's not a back arc. This would imply a morb basement. It could be a lochlanus from the Paleo-Pacific if it is sitting on an older arc or a continental fragment, but it can't be thrust over the Wagoromeo belt, as the abduction models suggest, as this would preserve some Wagoromeo basement, which should be high susceptibility. It can fit a west dipping model if the arc doesn't preserve or never had a significant amount of morb or back arc basement. Overall, the data are more consistent with the Lachlan Orogen model, but not uniquely. Let's put this in the larger setting of the early Paleozoic. The basement of the Macquarie Arc has an intermediate composition and is laterally and vertically extensive. The basement might be an earlier Cambrian phase of arc activity, suggested by latest Cambrian dates from the Kulak serpentinite and magmatic zircons from Monza and other localities. West of the Macquarie Arc in Victoria are other latest Cambrian Boninitic, Tholite, andesite systems, as upthrust elements of the mafic basement of the Western Lachlan. In the orocline model, these developed in a forearc setting. Further west again, three elements of the late Cambrian Mount Wright Menindee Staveley arc form a jagged line, with Tholite and Boninitic Tholite systems in their forearc. Mapping evidence dates bending in that line, and so some of the curvature in the western part of the orocline, to the Delamerian deformation at 500 MA. What does this signify? And there's what we think in New South Wales of as the elephant in the room, the mysterious Hay-Boolittle zone. Ross Cayley would see that as part of the Macquarie Arc. Let's think about the relationship in the late Cambrian between the precursor to the Macquarie Arc and the Victorian Boninitic Tholite system. If the Izu-Bonin arc is an analogy, that would put the Victorian Boninitic Tholite rocks in the forearc of a juvenile, rapidly retreating subduction system. Unwinding the orocline model puts these east of the later mature arc, so the juvenile pre-Macquarie system faced east. The forearc in the Izu-Bonin arc system is 100 to 200 kilometres wide, and a calc-alkaline arc and a high potassium rear arc developed later, features which sound much like the Macquarie Arc. How does this fit into the Lachlan orocline model? Well, the action in the orocline model comes later. Here we are concerned with the step from the Delamerian Mount Wright Menindee Staveley arc to the nascent Macquarie Arc. The Victorian Boninitic Tholite andesite sequences appear to be formed by extension in the former forearc during rapid trench retreat. This was followed by nucleation of a truly andesitic arc further back from the trench, which then grew laterally, analogous to the Izu-Bonin and New Hebrides arcs. Continuation of this system led to the Ordovician Macquarie Arc. As a cheeky modification to this model, we could add the Hay-Boolittle zone as a Cambrian indenter. Similar to, but earlier than, the Selwyn block that is the protagonist of the later Lachlan orocline. Bending of the Delamerian arc, curvature of the stall zone, and incorporation of the Hay-Boolittle zone behind a southward migrating healing subduction zone represents an earlier iteration of the same processes responsible for the Lachlan orocline. To summarise, although it is intraoceanic, the Macquarie Arc is not simply sitting on a morb substrate, as often depicted, but has an intermediate composition basement. That basement is probably late Cambrian and likely to be an early andesitic arc. The late Cambrian arc may have developed behind an initial phase of boninitic near-trench volcanism, behind a rapidly retreating trench, in a system analogous to the Cenozoic Izu-Bonin arc. And the Hay-Boolittle zone may have been a microcontinent, or perhaps an oceanic plateau, accreted at about 500 million years. And thanks very much.